So we're going to pick up on slide set 6, slide 9, right? So I put up that video 6, 1 through 8 for you to watch. So we're going to pick up on 9. All right, so we're going to look at the reactions of ketones and aldehydes. Now, a lot of this is review. Right? So we've gone over a lot of these reactions when we talked about how to make alcohols, but we're going to go into a little bit more detail into actually how the reactions work, right? A little bit of mechanism in here, right? So right, all of these additions to ketones and aldehydes, regardless of the mechanism, kind of come down to doing the same thing, which is you have your ketone or aldehyde, you have a nucleophile, and you have a hydrogen. And in the end, you end up adding the nucleophile to the carbonyl carbon, right, which will make blue, right? And you add a hydrogen to the oxygen. So effectively, you're adding H and U across your double bond, right? So it's kind of like when we added HBr to alkenes, we added H to one side, Br to the other. Here we're doing something similar. We're adding nucleophile to one side, H to the other side, right? The reason this works is when you look at a carbonyl, the carbonyl oxygen is slightly negative and the carbonyl carbon is slightly positive, right? And there's two ways to kind of explain this. One is that the oxygen is just more electronegative than the carbon, right? So it pulls electrons towards itself, making it negative, and taking electrons away from the carbon, making it positive. Or we can think about this in terms of resonance, right? We're able to draw a resonance structure where the electrons that are shared by the carbon and the oxygen all end up going onto the oxygen. And you get a resonance structure where you have O minus carbon plus, right? So now, just like when we did like thinking, processing, blue screen, beach ball. Wait, there you go. Just like when we did the dienophiles, right? We were like, oh, this carbon's, I can draw it positive in a resonance structure, so I'm going to say this carbon is partially positive, right? Same thing here. I have this resonance structure where my carbon is positive, so I can say it's partially positive, right? And so if you're a nucleophile, you want to add to the most positive thing that you can, right? Which is going to be the carbonyl carbon. Now, there are two mechanisms that we can use to do additions to carbonyls, right? There's the acidic mechanism and the basic mechanism. Basically, exact same setup as we had with epoxides, right? So we're going to start with the acidic mechanism. This is what we just drew a second ago. So you're going to start with a weak uncharged nucleophile for the most part. All right. And this nucleophile is too weak to add to the carbonyl carbon, right? Carbon oxygen double bonds are strong. This nucleophile doesn't have enough oomph to add to the carbonyl carbon and break that carbon-oxygen double bond. So what happens in the mechanism, right, is the first step is you've got acid in there. You're going to protonate your carbonyl oxygen. Now, that oxygen is way more electron deficient, right? It's got a positive charge, so it's going to pull even more electrons towards itself, right? And it's going to make this resonance structure where it gets rid of the positive charge, right? And gives that positive charge to the carbon, right? So what ends up happening when you protonate the oxygen is if up here this carbon's, an eeny weeny bit positive, down here it's way more positive, right? You've pulled way more electrons away from that carbon. That carbon is more positive, so it's easier to add to, right? If you're a nucleophile, you want to add to the most positive thing you can. As soon as we slap a proton on that oxygen, that carbon gets way more positive, right? So what happens then is now our nucleophile can add to the carbonyl carbon. Carbon can't make 5 bonds, so for the nucleophile to add, you have to push electrons up onto the oxygen, and that is going to make your product. Right, so we add the proton, that makes the carbonyl carbon easier to add to than our weak nucleophile can add to. Right. So what I like to point out in the acidic mechanism is when you're doing everything, you add the hydrogen first. Right, so the first thing you do is you add the hydrogen, then your nucleophile adds. Right. Under the basic mechanism, we switch that order. So for the basic mechanism, we have our nucleophile, then H plus. This is a strong charged nucleophile, right? I get the same product, right? I end up with my nucleophile bonded to my carbon, and I make an alcohol. But the way I get there is slightly different. So under basic conditions, since my nucleophile is charged and strong, it's able to add to the carbonyl carbon without any help. So this nucleophile is charged. It can add to the carbonyl carbon, push electrons up. And just like the basic epoxide reactions, we let the nucleophile do its thing. And then after all the nucleophiles added, I don't want O minus, I want OH. So I add an acid. And I get my product. So under basic conditions, you add the nucleophile first. Right? Acidic conditions, you add the proton. Right? You add the proton to the oxygen, then you add the nucleophile. Basic conditions, you add the nucleophile, then you add the proton. As you can tell, the basic mechanism, super easy. Add a thing, then add a proton. The acidic mechanism is pretty straightforward, but what ends up happening is the mechanisms get longer because a lot of times we end up having to stack these two steps or some version of them together 2 and 3 and 4 times. So the mechanisms look longer or they are longer for acidic mechanisms, but a lot of times you're just taking these two steps, protonate your carbonyl, add a nucleophile, and you do that over and over and over again to get to your product. So this kind of bare bones acidic mechanism is really important to know, because once we get to the bigger mechanisms, if you just see like, oh, that's an easy two-step mechanism, but I'm doing it 3 times, they don't look as daunting as if it's like, oh, this is like he used 3 iPad screens to do this mechanism. This seems really, really bad. But it's like, oh no, it's the same 2 steps over and over and over again. So just make sure you have this one really down. Okay. And something else I want to point out is in either case, either acidic or basic conditions, your acidic or basic conditions, aldehydes are more reactive, or are easier to add to than ketones. I should say, also you can just read that as faster. So aldehydes are more reactive than ketones. You're always going to add to them before you add to a ketone, right? And we're going to go into some like more detail as to why, but there's one like really simple thing that you can look at and think about that kind of explains this for most cases, right? You have an aldehyde, you have a ketone. Hydrogen is the smallest element on the periodic table, right? So if you're a nucleophile and your options are going past the smallest element on the periodic table or going past any other element, right? You're going to say it's way easier to get past the smallest element on the periodic table than it is to get by a carbon or to get by 2 carbons, God forbid, right? So if you're a nucleophile, you're just going to almost always choose the aldehyde to add to because it's way easier to get past the hydrogen. This we can call the bouncer theory, right? Bouncers are never 5 foot, like 110 pounds, right? Bouncers are always like 6'6", 240, right? Or just big people, right? And because like it's easy to get by someone in theory that's 5 foot, 110 pounds. Club's full, and you like pick them up and you set them aside, and you're like, not anymore. And you go in, right? Club's full. Got to pick up the 6'6", like 300-pound person, and you're like, mistakes were made, and then you're like in the parking lot, right? So hydrogen's just a bad bouncer. Hydrogen's like nucleophile, you can't come in here. Nucleophile's like, get out of my way. I'm gonna go add to this carbonyl carbon, right? Carbon's a better bouncer. Carbon's a little bit bigger, right? So the bigger that atom gets that's attached to the carbonyl carbon, the harder it is for the nucleophile to get by, right? Okay, so this last bit of stuff here is pretty much all review. Yay, right? We have our organometallic additions that we did for the alcohols, right? Have your carbonyl, you have, let's say, your Grignard reagent, right? If you remember, we could always break a carbon metal bond and say, hey, the metal is positive, the carbon is negative. So the negatively charged carbon adds to the carbonyl carbon, pushes electrons up. And you got your metal chilling out. And then you're going to protonate your oxygen. So I drew my magnesium bromide near my oxygen. The way that it most often gets drawn is it gets drawn as a bond. So these two things are equivalent, right? Saying like, hey, I have O minus and the magnesium is close to it, or I have the oxygen bonded to the magnesium. Like that still breaks down to O minus magnesium plus, but this is how you're most often going to see it, is where they're kind of all stuck together. Right? So all of these are doing the same thing, right? All the organometallics that we had, the negatively charged carbon is a strong nucleophile, adds to the carbonyl carbon, pushes electrons up, and then we add acid. For the bottom, so you get to the same place. The only thing that kind of changes is you just take the electrons from the oxygen magnesium bond and they go grab the hydrogen. Because they're the O minus electrons are the electrons that were used to make the bond to the magnesium. So we just use those again to go grab the proton. So we did all of our Grignard additions and stuff for alcohols. They all fall under this basic mechanism. I'm going to keep doing this one over and over again. Right, same deal. You've got your carbon minus, your metal's chilling out by it, and you add to the carbonyl carbon, push electrons up. Nope, didn't mean to make it aromatic. And then our H plus. Electrons go grab that hydrogen. And you get your alcohol. Right. The other basic addition you guys already know is the addition of hydrides, doing reductions. That's the other thing that you already know that we went over for alcohols, right? So you have your ketone or aldehyde, NABH4. Here, your nucleophile is H minus, right? So oftentimes I'll let you guys cheat, right? So NABH4. For most of these, I just say, like, just think of this as a source of H minus. We're not going to worry too much about the structure of it, but let's think of it as just a source of H minus. That H minus is our nucleophile. It adds to the carbonyl group. Oh, we'll say sodium on it. It can also be the boron, right? Then we add our acid, and that gets us to our product. right? But we went over 3 reagents before, right? We went over sodium borohydride, Diebol, and lithium aluminum hydride. They all just kind of default to being a source of H minus, right? So mechanistically, they're all pretty much the same, right? It's just we're changing the package that the hydride comes in. Right, so Diebol, just a source of H minus. Lithium aluminum hydride, just a source of H minus. The difference is how reactive that H minus is. Remember, sodium borohydride is the least reactive H minus, then Diebol, then lithium aluminum hydride is the most reactive source of H minus. So we're getting H minus in all the cases, it's just some of them are a little more reactive than others. But in the end, they're all doing the same thing. They're all adding to that carbonyl carbon and pushing electrons up onto the oxygen to make an alcohol. Right, so even though the reagents are different, they're still doing the same thing in the end, which is making H minus or giving us H minus so we can add it to a carbonyl group. So far, so good? So, all right, time for a few more examples. All right, so this is all pretty much just a review of the stuff we had done in the alcohol stuff, right? So what am I going to get for my first product here? So I have a hydride plus a ketone. It's going to turn into what kind of alcohol? A secondary alcohol. We're going to get a secondary alcohol here. We're going to add our hydrogen. So here, there. So what am I going to get for this next one? Ketone plus organometallic. I'm guessing it's an alcohol again. So I've got 2 carbons on my carbonyl carbon, and I'm adding a third. So what kind of alcohol am I going to make? A tertiary alcohol, right? Because I'm going to have 3 carbons now on the carbon that has the alcohol. Start out with 2 from the ketone, add 1 from the organometallic. All right. And now this last one here, aldehyde plus Diebol plus a hydride source. I'm going to, if I'm a gambling man, I'm going to say it's going to make an alcohol. What kind of alcohol? Primary. All right, so these are all basic conditions to do the addition to a carbonyl, right? And kind of the giveaway here is the then H plus, right? So very similar to additions to epoxides, right? The then H plus, for the most part, tells us we're under basic conditions. So there's a couple other reactions that work under basic conditions, and then we're going to move into acidic conditions for reactions. So the first basic condition reaction we're going to do is cyanohydrin synthesis. So the particular cyanohydrin we're going to make, they're going to look like this, right, where they're alpha hydroxyl nitriles. Right, so this is the alpha carbon to the nitrile, and on it we have a hydroxyl group. So this is our cyanohydrogen that we're going to make. Right. Now, the way these work is you have KCN and you add HCN, and that adds your CN to your carbonyl carbon. So we've talked about HCN before. It's real bad, right? You smell almonds for a little while, then you don't, then you die, right? In this reaction, the HCN is the solvent. So we actually have to end up with liquid HCN. Right, so we have to take this poisonous gas and we have to condense it into a liquid. You usually do this by kind of blowing it over dry ice. That will cause it to condense into a liquid, and then you have to keep your flask at dry ice temperatures so that your HCN stays a liquid so you can run your reaction in a literal flask of liquid death, right? Little sketch. Like this is one of those reactions I'm like, who would run this? So I made a joke when I was a postdoc. I was like, yeah, it's like, so this reaction, if your like advisor is like, yo, I'm leaving for the week, I need you to run this reaction, they're just hoping you're not there when they come back. I want to fire this person, but I'll just let them do this, and if they die, I don't have to fire them. Cool, easy enough. And this guy raised his hand and was like, well, actually, I've done that reaction, and it works really quite well. I'm like, maybe someone doesn't like you. Why, why is this a thing you're doing? He's like, well, I'm going to take this hydrogen cyanide, I'm going to condense it into this poisonous soup, and then I'm going to like run reactions in it. Seems awful. Right? So the way this works mechanistically, right, is pretty straightforward. Right? So our nucleophile here is our KCN. So you're going to have your KCN, right? And you can say, hey, my potassium is positive. The carbon of my nitrile is negative. That's going to add to my carbonyl carbon. I'm going to push electrons up onto my oxygen, right? Because I can't make more than 4 bonds to carbon. So to add that nucleophile, I need to push my electrons up onto the oxygen. So we're going to get here, we're going to have our O minus hanging out by our potassium to kind of balance it out, make that salt. That's not what we want. So here's where the HCN comes into play. So once we have that O minus, we're able to have it go out, grab the proton off of HCN. That makes our cyanohydrin plus regenerates KCN. So we're kind of cheating here, right? We've got our nucleophile and our acid in the reaction at the same time. But if KCN reacts with HCN, I end up making KCN and HCN again, right? So at no point do I ever like get rid of my nucleophile by the fact that I have acid around, right? My charged nucleophile, if it reacts with the acid, just makes my charged nucleophile again. So we kind of get the cheat there and have them in there at the same time. So this reaction works well with aldehydes. It's slow with ketones. Right? So as a general rule, so why is this, right? And sometimes will not work with hindered ketones. All right, so CN- is a weak nucleophile, right? It's a stronger nucleophile than like HCN, but compared to a hydride, an H minus from sodium borohydride, or the carbon, the negatively charged carbon of a Grignard, CN is not nearly that nucleophilic. So we're kind of right on the edge of these working, right? So when you have hindered ketones are hard to get to. So I'm going to put our hindered ketones. We're going to just take tertiary carbons. If you have a tertiary carbon in your ketone, right, these are basically slow to no reaction to make your life easier. We're going to say if you have a tertiary carbon on your ketone, the reaction is not going to happen. Right? The CN minus is not going to be a strong enough nucleophile that it's going to be able to get past, it's going to be motivated, if you will, enough to get past that tertiary butyl group to get to the carbonyl carbon. Right? Now, if I have an aldehyde, I have a tertiary carbon, right? It still has a really small hydrogen on one side, and it's able to react. But if it's a ketone, it's not going to be able to, it's not going to be able to react. I don't know if I actually drew the right product. It's not going to be able to react, right? So hindered ketones are too slow to react. The CN minus isn't a strong enough nucleophile to get past the steric bulk at that position. That makes sense? Okay. So we talked about this before, and we can kind of generalize and say that for any of these addition reactions that we're going to do, right, aldehydes, always do addition reactions faster than ketones, right? So you're always, if you have an aldehyde versus a ketone, your nucleophile is going to always add to your aldehyde first. And we talked about one reason this is, right? And we're going to add a second reason. So we're going to kind of revisit our first reason, right? So why is this? Why do aldehydes react faster than ketones? The first reason is, again, kind of our bad bouncer theory, right? Aldehyde, carbonyl carbons are easier to get to because of the hydrogen, right? Because the hydrogen, because the hydrogen is small, right? So You've got your aldehyde, you've got your ketone, right? Say the hydrogen is small, right? And then comparatively, any group that we put in place of that hydrogen is significantly larger, right? And if you're a nucleophile, right, it's easier for you to get past the small group than it is for you to get past the larger group, right? That just makes sense, right? That is back when we talked about like hydrogen's a bad bouncer. Does a very bad job of keeping nucleophiles out. It's not super intimidating. This is a kinetic argument. Right? This is based on how fast the reaction happens, right? How easy it is for the reaction to occur. So this is just based on rates, right? So this is a kinetic argument based on how quickly the nucleophile can add to the carbonyl carbon. And it can add to the aldehyde carbonyl carbon faster because it's easier to get past the hydrogen. There's another argument that deals with stabilities. And that's a thermodynamic reason for this. So reason one, aldehydes are easy to get to because the hydrogen is small, doesn't block anything. Second reason is products from aldehyde additions are slightly more stable. All right, so let's take a journey of stuff that you know and have blocked out. All right, got my carbonyl carbon here. My carbonyl carbons in both of these are sp2 hybridized. Got my nucleophile here. All right. What's the bond angle on an sp2 hybridized carbon? No pressure. I can't retroactively fail you from organic 1. So I should be able to for this, but you know. Starts with a 1. It is 120, right? So on your sp2 hybridized carbon, the two groups on your carbonyl carbon are 120 degrees apart, right? When you do your addition, I go from sp2 hybridized to now these are sp3. What's the bond angle on an sp3 hybridized carbon? There's a decimal in it. So we're super accurate. 109.5. Yes. Excellent. Zoom was also coming in off the top rope. It was great. It's great. We were doing a good job here. So when you go from an sp2 hybridized carbon to an sp3 hybridized carbon, the two groups that are on what was your carbonyl carbon is this blue carbon here, right? The groups get closer together, right? The hydrogen gets closer to that carbon group from the aldehyde, and these two carbons from your ketone, they get closer together, right? They get closer together and they increase steric interaction, right? But hydrogen's really small. So the difference between being at 120 degrees and 109.5 being ever so slightly closer is pretty negligible when you're a hydrogen, right? Because a hydrogen is the smallest atom. So getting it a little bit closer to that carbon from your aldehyde doesn't really increase the steric interaction that much, right? But when you move those two carbons closer together, you get a greater steric increase. So moving these two large groups together Okay, so moving two carbons together causes a greater increase in steric strain than if you move a carbon and a hydrogen close together. That means that this tertiary alcohol that we get when we add to our ketone is slightly less stable because you've got those two carbon groups kind of banging into each other a little bit, right? So this is a thermodynamic reason. Or making the secondary alcohol product is ever so slightly more stable than making the tertiary alcohol product. So these two things together, the fact that it's just easier for your nucleophile to sneak past the hydrogen to get to the carbonyl-carbon of the aldehyde, plus when it does, the product that you make has just slightly less steric interactions in it, makes it so aldehydes are going to react more quickly than ketones in pretty much every example we're going to do. Seem good? Excellent. Next up, hydration. So this is the addition of water to a ketone or aldehyde. The product that you get is a carbon that has two OHs on it. That product is called a hydrate. Now, under normal conditions, all ketones and aldehydes are in equilibrium with their hydrate, right? But if you just have a bottle of like acetone that you grab from the lab, right? That bottle of acetone, even though it has some hydrate in it, it is mainly ketone. So let's say we have our acetone here. All right. So if you have a bottle of acetone or any ketone, there's always an equilibrium with its hydrate form, but the equilibrium is going to favor the ketone. So again, this is a rough guesstimate. Say it's 99.9% ketone, 0.1% hydrate, right? So that bottle of acetone is pretty much all acetone with just ever so slightly a little bit of hydrate in it. Aldehydes, because they're a little more reactive, they too are in equilibrium, but the equilibrium favors the hydrate a little bit more, but it's still like 99% aldehyde, 1% hydrate. Right? So we may get a little bit more hydrate with the aldehyde, but not much. Right? And if you think about like what's going on here, it kind of makes sense, right? So when we first started talking about carbonyls, we said that carbon-oxygen double bonds are really strong, right? They're hard to break. We have to use really reactive reagents to break carbon-oxygen double bonds because they're strong. So if given the choice of having one carbon-oxygen double bond or the molecule having two carbon-oxygen single bonds, energetically, it's better if you have the carbon-oxygen double bond. It's more stable to be a ketone than it is to be a hydrate because of that double bond, right? So while we can make some hydrate, it's going to favor being the ketone because the ketone is just more stable, right? The aldehyde's a little bit more reactive, so while it still favors the aldehyde, you get a little bit more hydrate. But in the end, that carbon oxygen double bond wins out. If we change the structure of our ketone or aldehyde, we can influence the equilibrium and get more hydrate. The way that we do this most is if you have a ketone or aldehyde and you have an electron withdrawing group at the alpha carbon, right? The equilibrium is still going to favor the carbonyl in most cases, but you're going to get more hydrate. Right, so adding electron withdrawing groups makes more hydrate. And this makes sense if you think about, let's do like kind of the ultimate example here. Let's have CF3, right? Our most electron withdrawing atom, right? What does this do to the carbonyl carbon? Well, these fluorines are going to pull electrons towards themselves, and they're going to cause this carbonyl carbon to be really partially positive, right? They've pulled electrons, the fluorines pull electrons towards themselves, which makes the carbon more positive. Versus if you just had like acetone, you'd have a little positive charge, but not nearly as positive as you have those electron withdrawing groups. So if you're water and you're picking a carbonyl carbon to add to, you're going to add to the more positive one, right? Right? So that means you're going to make more hydrate because it's easier for water to add to the more positive of the two carbonyl carbons. Right? So by adding electron withdrawing groups, you make your carbonyl carbon more reactive, which in turn leads to you making more hydrate. Seem good? So hydration is kind of this, kind of our bridge between acidic mechanisms and basic mechanisms, right? So it works under both acidic and basic conditions. So we're going to do the acidic mechanism, sorry, the basic mechanism first, then we'll do the acidic mechanism, and that will get us into the rest of our acidic mechanisms that we have to go over. Right, so the basic mechanism is very similar to the addition of like KCN with HCN. So you're going to have like sodium hydroxide and water. Right, this could be any hydroxide. I have sodium hydroxide. It could be lithium. It could be potassium. Right, as long as you have a hydroxide, and then with water. So it's kind of the same thing where we had KCN with HCN. Here we have hydroxide with water, right? I have the acid, and then the base. And then it's not gonna be green. That's gonna make your hydrate. So I did this on your nitrile addition, and I'm going to point this out as I go forward, right? So when I do this addition, I'm going to point out that each step in this mechanism is in equilibrium. It can go forward, but it can also go back. So we're going to get to right? So when we add a hydride, right, H minus, or we add a carbon nucleophile like a Grignard reagent to a carbonyl carbon, that reaction only happens in one direction, right? We add the nucleophile and we get our O minus, and it can never go back. When we add hydroxide here, this compound here could collapse back to the what's it called? Head not working. Could collapse back to the ketone and spit the hydroxide back out. So all of these steps are in equilibrium. They go forward or they can go backward. Right? Now, just like we did with the cyanohydrin, my O minus is going to grab a proton from water, right? A proton from the acid that's in solution. It's acting as a solvent. And then regenerate sodium hydroxide. Get up a product and regenerate sodium hydroxide. So, since these steps are in equilibrium, we have to do something to make sure that we get the product that we want, right? We've got to ensure that we get hydrate and we just don't keep going back to our carbonyl starting material. So remember Le Chatelier's principle? Gen Chem, I know, spooky, right? Le Chatelier's principle says if there's a reaction in equilibrium, if you add something to the starting material side, it's going to force the reaction towards products. If you add stuff to the product side, you're going to force it back to the starting materials. So typically, when we do these hydrations, we use a large excess of water, right? Because now we have a lot of water on the starting material side of the reaction, which is going to force our molecules to make hydrates. Right? It's going to push us towards our product. So water is often a solvent or just in large excess to force these reactions to go. So here we use water and catalytic acid, and this will make a hydrate. Now, I'm either going to just like give you the generic catalytic H plus, or there's a few acids that show up in here and in acetal formations. So sometimes you might see this as toxic acid, TSOH, PPTS, or occasionally sulfuric acid. These are the two biggies that are going to get used the most, right? But it's either going to be the generic catalytic H plus, or it'll have one of these acids as the catalyst. Right? The mechanism, right? The first thing we have to remember, right, is when we have water and acid, what's going to happen first is the water is going to react with the acid to make H3O plus. So the acid that we're adding doesn't actually ever react with the carbonyl, doesn't ever react with the ketone or the aldehyde. It reacts with the water, and then that is then what reacts with the ketone or aldehyde. So the first step is your water is going to react with your acid, to protonate your water, right? This is just H3O plus. So you're making your H3O plus in the first step. Now that you have that H3O plus, that is what actually is going to react with the carbonyl oxygen. So now we're going to protonate that. and generate water. Water is a bad nucleophile, and now that I've put a proton on the carbonyl oxygen, I'm able to add that oxygen to the carbonyl carbon, push electrons up, right? Now the only thing at this point standing between me and my hydrate product is removing an extra proton, right? I have one extra proton on my oxygen. So another molecule of water can come in, grab a proton, give me my hydrate plus my H3O plus, right? So the reason I get to use two waters in my mechanism is that, remember, water is going to be in a large excess because I need extra water to push the reaction towards being a hydrate. So I just have a lot of extra water laying around. Seem good? So what am I going to make for the first thing? Gonna make a hydrate. So where my carbonyl is, I'm just gonna end up with two alcohols, right? Carbonyl carbon becomes hydrate carbon.
The question was, what about the H3O plus generated in the first reaction?
I do make H3O. I will end up making H3O plus, but right, the general rule is if it's water soluble, I don't care about it. So you don't have to show the H3O plus as a product, but you do. It is there. But right, if you think about how you actually would like run this reaction, you'd like make the hydrate, you do some sort of workup to get rid of the acid and just leave you with the hydrate. So we're not going to worry about the H3O plus as something you need to draw as a product. What about the other one? What am I going to make for the next one? Hydrate again. These are so easy. Or you're just very smart, one of the two. We'll go with very smart. They're very difficult. You're all very, very smart. That, yeah, it was said with some sarcasm in your voice, and I'm just trying to build you guys up. I'm trying to build you guys up so you're like, oh, I feel good about my life choices. I'm glad I spent $20,000 a year to come to school here. Wakefield makes me feel good about myself. Right? If I was like, you're all dumb, you'd be like, I really regret spending $20,000 to have someone yell at me and say I was dumb. And you wouldn't want to do that.
The question was, do we get the same products under acidic and basic conditions?
Oh yeah, so like I took this and just changed it to the acidic conditions, right? If I was just like, hey, this is now water and a catalytic acid, yes, you're gonna get the exact same thing, right? It'd be the same for all the ones for the hydrates because they can be either acidic or basic, right? Big picture, maybe your molecule isn't stable in acid but is stable in base, so that's why you'd pick the basic conditions over the acidic conditions. But on simple molecules like these, like you're gonna see, the conditions are gonna be interchangeable. All right, so what am I gonna get here? Joke's not on me. It's an aldehyde, so reaction. Yeah, I'm gonna make the cyanohydrin. So I'm gonna add CN to my carbonyl carbon. For the most part, I'm not gonna give you like a no reaction thing on the exam. So I give you that as an option. You're just gonna put that for everything. I've run the experiment. It's rough. If on every multiple choice one, I just put no reaction, like someone would just be like, none of these work. This is all a lie. Chemistry is a construct, man. And I'll be like, all right, calm down. So we're gonna start with acetals. We're not gonna get through the mechanism, but we're gonna at least start on it. The easiest way to think about these are hydrates, but with alcohols, right? So an acetal, right? You're gonna have your carbon is going to have two O carbon chains on it, right? So normally it's going to be something where you have, say, you have an alcohol, and then you have catalytic acid. These I'm more than likely going to use either Tosic, uh, PBTS, or sulfuric acid. These are the acids that I use the most for these. So here I'm way more likely to put one of the acids than I am to put just catalytic H plus. Usually Tosic acid or PBTS. So again, these are the two biggies that get used the most. And then this is going to make your acetal. So Ether Bunny, you can't unsee that now. You 100% can't unsee that. I also found a good meme that's going to go in the video. It says the Ether Bunny's coming for you, and it's like the Easter Bunny putting a rag over someone's face, like kidnapping them. There you go. There's the Ether Bunny. I gotta get those YouTube bucks one day, man. Enough people are watching videos. I want to get my hours watched up. I just need more subs. I need 1,000 subs. Tell your friends. Like and subscribe.